Hi, I hope you're doing well. This is Dr. Golding again. We're going to be talking about 6.4 in the book. In section 6.4 in the book, we learn about how to do truth tables for arguments. Now, I don't need to remind you about this, but I'm sure you recall that the way we define an argument is that an argument is an attempt at rational persuasion, but we gave a bit more substantial definition of an argument. An argument is a series of steps in which you have premises and you have a conclusion, right? So you have a list of premises. It could be just one premise, but often it's more than one premise. And we always have, at least according to the book, there's got to be one conclusion per argument. So an argument is a series of steps or statements in which you have premises and then you have a conclusion, and there's a claim made that somehow the premises lead logically to the conclusion. And if you remember, we defined an argument as deductively valid if it is impossible for the premises to be true and the conclusion false at the same time. So now what we're going to do, now that we've developed a symbolic language, we're going to be able to show that certain arguments are valid and certain arguments are invalid using the truth table method. So the basic strategy of the truth table method is you're going to, and I'm going to do some examples on the board, but the basic strategy is that you're going to list all of your premises and your conclusion on one horizontal line. Then you're going to do a truth table for that entire line, and then you're going to examine whether you can find a single row where all of the premises come out true and the conclusion comes out false at the same time. If there's at least one row where all the premises come out true and the conclusion comes out false, then that will have shown that the argument is invalid. If there's not a single row where all the premises come out true and the conclusion false at the same time, that's going to illustrate and demonstrate that that argument is valid. So basically, your exercises at the end of 6.4, I'm going to ask you to do a few from Roman numeral 1, like 1 through 5 of Roman numeral 1, and from Roman numeral 2, do all of them except for, there's a few of them that have 4 components, and that gets messy and hairy, and it's too long for us to bother with that right now. So I'll tell you specifically which ones those are, but let me write down the homework in case you just want to jump into this yourself and don't want to bother listening to the whole video. If you get it from the book and you can do the exercises, that's fine. But here's what I'd like you to do for homework. We're talking about 6.4 and Roman numeral 1, do 1 through 5. As you'll see, in Roman numeral 1, you're given arguments that are in English, and you have to translate the arguments into the symbolic language, and then you have to do a truth table for each argument and see whether it's valid or invalid. I will do a couple of those, but then focus more on Roman numeral 2. And I'd like you to do all of Roman numeral 2 except for, one second, let me look at my book. Okay, all of Roman numeral 2 except for number 12, 17, and 20. I'll write that down. All except for 12, 17, and 20. I'll explain more of the reason about why I'm letting you off on doing 12, 17, and 20. But for now, let's show you a couple of examples of how to demonstrate that a given argument is either valid or invalid. I'm going to start off with some pretty simple examples, and then we'll do some examples that are a little bit more complicated and nasty. And eventually I'm going to show you that there is a certain shortcut method to doing some of these problems, which is something that would be helpful on an exam, for example. All right. Here is an example of an argument that's pretty simple, and my luck in guessing last time was pretty bad, but I'm going to go out on a limb and say that I really believe that this argument is valid. Look at this argument. It's a very simple argument. Suppose I have P wedge Q, not Q, therefore P. Suppose somebody gives me this argument. Okay, this says either P or Q is true, not Q is also true, therefore P has to be true. Now, if you just think about this, this should be valid because you have a disjunction, either P or Q has got to be true, at least one of them is true. This premise comes along and says, well, Q is not true. Well, that means P better be true. So I'm pretty confident that this is a valid argument. The nice thing about the truth table method is that now we have a way of displaying, of proving, indicating that this argument definitely is valid using the truth table method. Okay, so now how would I do a truth table for this example? Well, you have to rewrite them in the form of a horizontal line. That's the first thing. We're going to do like this. We're going to go P wedge Q, not Q, therefore, and this little sign with the slash and then the 3 triangular dots indicates that the conclusion is coming, the conclusion is P. All right, we write them on a line. Then we make a cross. Always make a cross like this. And now I'm going to list in alphabetical order all of the simple components. Remember, a simple component is a single letter, P, Q. All we have here is P and Q, right? I'm going to list all the simple components that are in this argument in alphabetical order. So I would have P and then Q. And now I'm going to list all the possible combinations. Now, when you have 2 components, there's going to be 4 possible combinations. Standard way to write them, T, T, F, F, T, F, T, F. Okay, those are the 4 possible combinations for P and Q. Now I'm going to do a truth table for each of these formulas separately, but keep them on the same line. So for example, what is P or Q here? When P and Q are both true, the wedge is true, right? It's going to be true, 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 and only false on the last line. How do I know that? That's just the definition of the wedge, okay? Now I'm going to try to keep my line straight. I think I sometimes have a little difficulty doing that. It's better if you're doing this on lined paper. If I had a lined chalkboard, that would be better. But I'll do my best to try to keep these lines aligned. All right, so now not Q. I need to do not Q. So not Q is going to be false, true, false, true. And what's the value of P? Well, the value of P is whatever it is over here. So it's T, T, F, F. T, T, F, F. Okay, I've done my truth table for the argument. Now what I have to do is see if I can find a counterexample. Now what is a counterexample? A counterexample in this context, a counterexample is a row on the truth table where all of the premises come out true and the conclusion comes out false on that same row. Do I find a counterexample here? Okay, so I have to look for where is there a row, or is there a row where all the premises come out true? There's only one, it's this row. On this row, both premises come out true, and on that row, the conclusion also comes out true. So that means I'm going to say no counterexample. There's no counterexample. There's no row on the truth table where all the premises come out true and the conclusion comes out false. And that means, therefore, the argument is valid. That's the basis of this whole thing. Truth table for the whole argument on one row. Look for a counterexample. If there's one counterexample, the argument's invalid. If there's no counterexample, the argument is valid. The rest of it is basically doing this with more complicated formulas. So I'm going to pick something from the book. I'm going to do one of the exercises. Let's try number 4. We're going to do, this is from Roman numeral 2, number 4. At the end of 6.4, Roman numeral 2, number 4. So let's do that one. I'm going to have to get it up here on the board, so give me a minute. This involves G and M as opposed to P and Q. Doesn't really matter. G and M, so I'll put M here and G here. No, alphabetical order, G and then M, right? So you have G and then M. Let's erase this. We have not G dot M That's the first premise. I hope you can see. I hope the glare is not bothering you from the board. This says not, parenthesis G dot M. The second premise is M wedge not G. We don't need parentheses around there, but I'll leave them up. Now remember, these are two separate premises, all right? So leave a little space in between here, otherwise we'll get all confused. The conclusion here is not G. So I'm going to do my little symbol. Here's the conclusion is not G. Okay. Now with M and G, well, I wrote G and M in alphabetical order. There's 4 possible combinations. We're supposed to list them in this way. Now we got to do each premise separately. So I have not G and M. So what should I do first? I should do the dot first. G and M is true over here and false everywhere else because it's a conjunction. So not G and M is going to be on this row, it's going to be false, true, true, true. Not G and M is going to be false on the top row, and it's going to be true on every other row. Now if I want, I can make a little sort of circle around here indicating that this is the value of this formula, FT, T, T. Okay? Already I'm getting my lines misaligned, I see, but I'm going to do the best I can. Okay, what about M wedge not G? Okay, well let me go ahead and do not G first. So not G is going to be F, F, T, T. M on this row, I'm going to copy it over. We get T, F, T, F. So that's the value of, no, I'm sorry, this is an F. It's very easy to make a simple mistake, unfortunately. So that is the value of M. I'm simply copying over T, F, T, F. Now I have a wedge. So the wedge is going to be true, false, true, true. This is the value of the second premise, T, F, T, T. And now I get to my conclusion. The conclusion is not G. So not G is going to be the opposite of whatever the value of G is over here. So we'll get F, F, T, T. F, F, T, T. So this is the value of not G all the way down. Now, the next step is what? It's to look for a counterexample. A counterexample is what? One row, at least one row. If there is at least one row where all the premises come out true and the conclusion comes out false on that same row, then we have a counterexample and the argument would be invalid. We would have shown that it's possible for all the premises to be true and the conclusion false at the same time, so therefore the argument would be invalid. Well, over here, I see that on this row, well, this is not a row where all the premises come out true. This is not a row where all the premises come out true. On the two bottom rows, the premises come out true. So over here and over here, the premises come out true. But lo and behold, the conclusion also comes out true on that row, right? T, T, T. All right. T, T, T. And I have on the bottom row, they also all came out true. That means it's impossible, given these premises, it's impossible. There's never going to be a case, no matter what G and M stand for. Okay, G could be Dr. Golding lives on the moon, and M could be the moon is made of green G. It doesn't matter what M and G are. Even if M is false, G is true, G is false, M is true, it doesn't matter. It's impossible, given the structure of these premises and the structure of that conclusion, it's impossible for the premises to be true and the conclusion false. So therefore we would say no counterexample. And therefore the argument is valid. Now, let's try an example where you have three components. If you have three components, your truth table is going to have 8 rows. If you have 4 components, it's going to have, I think it's 4 squared, it's going to have 16 rows. So that's why I'm going to ask you to skip numbers 12, 17, and 20. I mean, I'm asking you to skip them because I'm letting you skip them because they're 16 rows. And that's just very messy. And it's just, I mean, just going to let you off on any example that has more than 3 components. Okay, so, but let's try one with 3 components. Let's take a look at, it looks to me like number 8. Let's do number 8. We have, let me get on, I have to erase this, going to have to write smaller and try to get 8 rows going here. So let's try this. And if you're getting a little bored of watching me, you could try doing this yourself. Try doing a truth table for number 8. Again, we're in Roman numeral 2. So try doing a truth table for number 8. Maybe you can shut the video off for a second and try to do number 8 yourself and see what you come up with, and then you can watch me and see if I get it right. Anyway, here's number 8. It says C biconditional D. And we have E wedge not D. And we have as a conclusion E horseshoe C. Okay, the first step is to make sure that you copy the example correctly. That's very important. Otherwise, you're not doing it right. Makes sense, right? Okay, C biconditional D, E wedge not D, and then E horseshoe C. Now the next thing is I make a cross. That line is not very straight. Let me fix that a little bit. Okay, next step, I list the components in alphabetical order, A, B, C, D, E, right? C, D, and E. Now I'm going to have to list all the possible combinations of whether C is true, D is true, D is false, E is true, they're all false, they're all true. There's going to be 8 combinations. The standard way of doing this, and you're supposed to do it the standard way, is you do 4 T's in a row and then 4 F's in a row when you have 3 components. 4 T's and 4 F's. Then you do 2 T's, 2 F's, 2 T's, 2 F's. And then the last one, the third one, you alternate T, F, T, F, T, F, T, F. T, F, T, F, T, F, T, and F. Okay, so those are all the possible combinations of truth and falsity when you have 3 components in your argument. Now, you go to each component, and then you do the truth table for each formula. So, the main thing here is to make sure you're looking at C and D. Those are the first 2. It's going to be true whenever they're the same. Remember the definition of biconditional is that it's going to be true whenever they have the same value and false whenever they're different. So therefore it's going to be true on the top 2 rows. Let me try to keep my rows straight. F, 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 and then on the bottom, both C and D are false. So therefore the biconditional is true. Okay, so that's the value of C biconditional D. Now I need to do E wedge not D. Now let me do not D first. So D was TTFF, TTFF. That means not D should be the opposite. It's going to be F, F, T, T, F, F, T, T. That is the value. I'm trying to write that row under the tilde over here. Okay? It looks like I've written it a little bit under the wedge, but this is the value of not D. Maybe I'll move this over, make this clear. This is F, T, T. All right, that's the value of not D all the way down. Now I need to do E wedge not D. That's going to be, I know it's going to be true here because this is true. I know it's going to be true here because this is true. This is true. All right, but E is true on this row, so that means this is going to be true. This is going to be true. This is going to be true. What about on these 2 rows over here? Well, here, E, okay, see, I made a mistake. Excuse me. I was looking at C. I should have been looking at, let's do this. I need to do this again. I made a mistake because I was looking at, that's unfortunately easy to do. I was looking at C. I need to look at E here, right? E is true here, false here, true here. Let me just go ahead and write down the whole value of E. Sometimes that's just the easiest thing to do. This is going to be false, true, false. Okay, so I've got TF, 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 TF. That is the value of E. Now I'm looking at E wedge not T. It's true here, false here, true, 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 false. This is the value of E wedge not D for all 8 rows on the truth table. Okay, true, false. I'm just checking this out to see if I copied over correctly. Okay, I think I've got this copied over correctly. It's actually a little easier to do when you're doing it in your notebook and you have the lines right in front of you when you're on the board. It's easier to get distracted as I have done. 1 second. Okay, now I need to do the conclusion, E horseshoe C. Now again, it's easy to get messed up here because you're doing E horseshoe C. So that means I'm just going to write down, for the sake of my own sanity, I'm writing down the whole value of E, all the values of E. Try to keep them aligned here. This is the value of E, and the value of C is 4 T's, 4 F's. Okay, now I'll do E horseshoe C. It's going to be true, 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 false. Remember, the horseshoe is false when you have antecedent true and consequent false. So it's going to be true and then false here and true here. So this is the value of the horseshoe, E horseshoe C. And now I need to see if I can find a counterexample. Well, there's only 2 rows where the conclusion comes out false. So I know that these are not counterexamples because a counterexample by definition is a row where all the premises come out true and the conclusion comes out false. If the conclusion comes out true, I don't even need to look to see what the premises came out to be because I know that on those 4 rows there is no counterexample. The only possible counterexamples will be on this row and this row. Because here the conclusion came out false and here the conclusion came out false. Okay, so we're looking at the 5th row and the 7th row. 1, 2, 3, 4, 5 on the 5th row. Well, here the conclusion came out false. I'm sorry, this premise came out false. So this is not a counterexample because here one of the premises came out false. What about on this row? Here the conclusion came out false. This is true and this is true. So indeed we found a counterexample. On the 7th row, I'm counting, this is the 7th row, this is the 8th row down here. On the 7th row, C biconditional came out true. They were both identical, so C biconditional is true. Over here we have E wedge, not D. E is true over there, so the horseshoe is going, so the disjunction is going to be true. Over here we have E horseshoe C, T horseshoe F. So if I were doing this on a test, I would say something like, I would circle this whole thing, and I would say, counterexample. I have shown that this indeed is invalid. If you find one counterexample, if you find more than one counterexample, then it's also invalid. So this is how you do a truth table for a formula, or rather, sorry, for an argument that has 3 components. Okay, what I'd like to do now is do a couple of exercises from Roman numeral 1. Now, in Roman numeral 1, you're given English sentences. So you have to do 2 things. You have to translate the argument. Now, we haven't done translation in a little while, so we might be a little rusty on our translation skills. But that is something you're supposed to know how to do. Translate English sentences into propositional logic. Then once we have the argument translated, we're then going to run the truth table method to see if those arguments are valid. So let me try to do, I'm going to do something pretty simple. I'm going to do let's do number 1. Okay, I'm going to do number 1 from 6.4 Roman numeral 1. Give me a moment to erase the board. Now, since I'm assuming you have the book, and I'm assuming that hopefully your example is the same as the one in my book, It reads like this. If national elections deteriorate into TV popularity contests, then smooth-talking morons will get elected. Therefore, if national elections do not deteriorate into TV popularity contests, then smooth-talking morons will not get elected. Now, if I read that argument, I might scratch my head and say, is that valid? Maybe I don't know if it's valid. So I'm going to use the truth table method to determine whether this argument is valid. So I need to translate the sentences into propositional logic and then do the truth table method. So what we have here is basically, we have to identify the simple components. Remember, that's what you do when you translate, is you have to identify simple components. Then you have to assign a capital letter to stand for each simple component. So we've got really two simple components. If you look at this, you should be able to see that. We have national elections deteriorate into TV popularity contests. So I'm going to let N stand for national elections deteriorate into TV popularity contests. Remember, when you're doing, when you're identifying a simple component, you want to take out any ifs, ands, nots, buts. You want to strip it down to a component that doesn't have any logical operators in it, excuse me. So N is going to stand for I'm saying. You could pick a different letter, obviously, but N is a good letter to choose because it reminds us of the first word. National elections deteriorate into TV popularity contests. I'm going to let S stand for smooth-talking morons will get elected. Smooth-talking morons will get elected. Now, do I have any other components in this argument? The next sentence says, then if national elections do not deteriorate into TV popularity contests, then smooth-talking morons will not. Those are negations of these two sentences, right? So these are the only components in this argument. So it's an argument that has two components. Now I need to symbolize the argument. So what we have here, there's really just one premise. It's N horseshoe S. If N, then S. That's the premise. And then the conclusion is, therefore, if national elections do not deteriorate into TV popularity contests, then smooth-talking morons will not get elected. We have not N, horseshoe, not S, right? If it's not the case that national elections do deteriorate into TV popularity contests, then it's not the case that smooth-talking morons will get elected. So that is the argument in symbolic language. There's one premise, N horseshoe S, and the conclusion is tilde N horseshoe tilde S. So now we're going to do a truth table for, now I'm going to erase this just to make room. I mean, ideally this is what you would do, is because you're assigning a capital letter for each simple component. So I wrote out the whole sentence. It's pretty obvious what each simple component stands for. But now I'll do a truth table for this. So I'm going to lower this down a little bit. It was N horseshoe S, therefore not N horseshoe not S. Make a cross. Write the components in alphabetical order. So we have L, M, N, and then S. With two components, there's four possibilities. T, T, F, F, T, F, T, F. Right? And horseshoe S is false only on the second row, true otherwise. So sorry, this is false, true, and true. This is the value of the premise. What about not N, horseshoe, not S? Not N is going to be false, false, true, true. All right, I'm doing not N over here. This is N, and this is not N, F, F, T, T. Not S is going to be the opposite of S over here, so this will be false, true. Now I do the horseshoe. This is true, true, false, and true. This is the value of N horseshoe S. Now, next step, look for a counterexample. Can I find a row on which all of the premises, now in this case there's only one premise, so can I find a row where the premise comes out true and the conclusion comes out false at the same time? Indeed, I see one right over here. Here the premise comes out true, and here the conclusion comes out false. So this row right over here is a counterexample. It is possible for the premises to be true and the conclusion false. So I say counterexample, invalid, that's what you got to do with Roman numeral 1. Let's try another example from Roman numeral 1. Let's see, I'm going to do, I know that this is in the book, but I'm going to do this I'm going to do number 4, okay? So, let me do number 7. I'll do number 7. I feel like doing number 7. You can try number 4 on your own. So number 7, let me erase the board here. Hopefully it doesn't have more than 3 components. It probably has 2, I'm guessing, but we'll see. Let's see what we got here is Einstein, this is again number 7. Einstein won the Nobel Prize either for explaining the photoelectric effect or for the special theory of relativity. So really there's 2 sentences in there. There's 2 simple components. Einstein won the Nobel Prize for explaining the photoelectric effect. That's 1. And then you have Einstein won the Nobel Prize for explaining the special theory of relativity. Those are 2 different sentences. So I'm going to let N stand for, I'm just going to say this out. N is going to stand for Einstein won the Nobel Prize for explaining the photoelectric effect. Maybe I'll let P stand for that, okay? Let me change that up. P reminds me of photoelectric effect. So here's what P stands for. Einstein won the Nobel Prize for explaining the photoelectric effect. And then I'm going to let S stand for Einstein won the Nobel Prize for the special theory of relativity. Now the next sentence says, but he did win the Nobel Prize for explaining the photoelectric effect, which is basically P again. The conclusion is Einstein did not win the Nobel Prize for the special theory of relativity. That would be not S. So there are only 2 components in this argument. P, again, P is standing for Einstein won the Nobel Prize for the photoelectric effect. S is standing for Einstein won the Nobel Prize for the special theory of relativity. There are no other simple components in this argument. So now I need to symbolize what this is saying. The first premise says basically P wedge S. So I'm going to put that right here. We're going to have S and P. Well, P comes first and then S. So we have a disjunction, either P or S. And then we have the second sentence is, but he did win the Nobel Prize for explaining the photoelectric effect. That would be P by itself. And then the conclusion is, therefore, Einstein did not win the Nobel Prize for the special theory of relativity. That would be, excuse me, therefore, not S. Okay, now then, I can erase P and S here. Now, I have a very sneaking suspicion that this is an invalid argument because this is a disjunction, and we know that a disjunction, in our language, a disjunction can be true even if both are true. So this is a disjunction. This goes ahead and says P, therefore not S. I mean, maybe P is true and also S is true. So I really am very confident that this argument should turn out to be invalid. Okay, so P wedge S is going to be true, 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 and then false. P is going to be true, true, false, false. All right, just copied over the value of P. So this is the value of the first premise. This is the value of the second premise. Now we have not S is going to be the opposite of whatever S is over here. So it should be F, T, F, T. Is there a counterexample? Yes, there is. On the top row, we see that the premises come out true and the conclusion comes out false. So my suspicions were correct. There is a counterexample, and it's invalid. The thing that's nice about this method is that you can prove that something is either valid or invalid. It's not just a matter of, it seems to me like this is invalid. There's a way of demonstrating that this argument is invalid. Now, I'm just about done for today. I mentioned something earlier about a shortcut for doing truth tables. This becomes especially handy when you have a lot of components and a lot of rows. Basically, what I had in mind there is when you do a truth table for an argument, sometimes it's a nice thing to start off with the conclusion. And then once you do the conclusion, you look at all those rows where the conclusion is false. Because on those rows where the conclusion is true, you know you're not going to find a counterexample. So you can basically ignore them. Once you've shown that on those rows they come out true, on those rows the conclusion comes out true, you don't need to examine what the premises come out to be. Maybe I'll do one more example and use a little shortcut method, okay? So let me get back to my book for a second here. Excuse me one moment. My book's falling apart. In any case, let's see here. How about, let's try, let us try number 7. I'm now going to Roman numeral 2, number 7. All right. Here you're just given the formulas and you got to run the truth table method through. I believe that this has, well, this only has 2 components. We have not w dot not x. Let's see here. Not w dot not x. That's, I'm doing number 7. Not w and not x. Then we have not x and not w. And the conclusion is x wedge w. Okay, so we only have 2 components here. Wx. W, X, Y, Z. So W and X. These are the possible combinations for W and X. I hope you are not having any glare on the board preventing you from seeing the table over here. To do a shortcut method on this, I would say to myself, look, X wedge W is going to be true. Look at this. This actually is a good example for a shortcut method because X wedge W is going to be true, true, true. It's only false on the bottom row, correct? So I automatically know that there's not going to be a counterexample in the top three rows. So therefore, I don't even need to look. I don't need to compute the values of these two premises on the top three rows. The only possible place where there would be a counterexample is over here. Okay, so all I'm going to do is compute the value of the premises on the bottom row. So not parenthesis W not X. Let me do this carefully. I'll do the not X first is true. The W over here is false, right? W is false, so the dot comes out to be false, but then the tilde comes in and makes that true. So on the bottom row, it is true that it is not the case that W and not X. Let me just check that again. X was false, therefore not X is true. W is false, therefore F dot T is F, and the tilde comes along and says true. So now I have to look at this premise. If this came out false, I wouldn't even have to look over here because I would know that there's no counterexample. Remember, a counterexample is a row where all the premises come out true and the conclusion comes out false. So if this came out false, I could already say, oh, no counterexample. But this came out true. That means I have to look at this one. So let's do this carefully. Not W is going to be true. On this row, X is false. So the dot comes out false. The tilde comes in and makes that true. So I see here that on the bottom row, this premise came out true, this premise came out true, but the conclusion came out false. I would say, okay, counterexample. Counterexample and invalid. But at least I saved myself some work. I didn't have to do the three rows here because only on this row was this false. Therefore, the only possible counterexample could have been on the bottom row. It turned out that there was a counterexample on the bottom row, but I took a shortcut and saved myself from having to do the top three rows, at least for the premises. Okay, so basically, that's going to be it for today. Homework again is to do Roman numeral 1, try to do 1 through 5, and if you feel like doing another one or two, that's great. In Roman numeral 2, try to do all of them except for 12, 17, and 20. Those examples have 4 components. The truth table is going to have 16 rows. Well, the nice thing, I think it's nice, I don't know if you think it's nice, I think it's nice, is that when we get to Unit 7, God willing, we should all be alive. When we get to Unit 7, we're going to learn a different method for proving that an argument is valid. So, but let's not get ahead of ourselves. I think we've done a lot for today. Again, try to do the exercises. If you'd like to email me your exercises, some of you have been doing this, that's great. That would be a very good idea to do. If you're having any trouble, you can email me. I also have given you my phone number, so you can call me if you need any assistance. So I wish you all the best health, stay strong, and try to be happy and keep your sense of humor during these stressful times. And again, if you need to contact me for any reason, please do so. Otherwise, look forward to another video going on with 6.5, I guess, is the next section. Have a good day.